I think it's time for our section. So good morning, everyone. Welcome to attend the AI-driven network section this morning. And in this section, we are pleased to invite 4 speakers who each share their experience on AI-driven network research, operation, and maintenance. So the first speaker is Harvey Newman from California Institute of Technology. The title will be Global Network Advancement Data Intensive Science W Update. So welcome.
Thank you. Thank you for inviting me.
So you might share your screen.
Okay, if you'd like me to start, I'd be glad to do so.
Yes.
Okay, can you see my screen well?
Yes.
Okay, so thanks for inviting me. I'll give an update on the Global Network Advancement Group with a focus on the Data Intensive Sciences Working Group. But before I do that, I'll also show some of the challenges which have motivated the formation of this working group, and also the big agenda that we have to develop a next generation system which integrates networks with site computing and storage facilities, and also proposes a new mode of operating and managing research and education networks. So among the data-intensive science programs, at the moment, the Large Hadron Collider program is the largest program in scale and perhaps also global extent. But these challenges are shared by other major programs, such as the Neutrino program at Fermilab, the Square Kilometer Array, the Vera Rubin Observatory, which is based in Chile, and others. So we have known for a long time that networks would not be able to keep up with the exponential growth of the traffic generated by these data-intensive programs. For example, for the LHC, the rate of growth is an increase of 40 to 60% per year. This really came to the fore in a meeting at the beginning of 2020, when the LHC experiments came forward and expressed the need for terabit per second links on the major routes. This is in particular in preparation for the second phase of the LHC program, called the High Luminosity LHC, which is scheduled to start in 2029. But in the meantime, we expect to see this exponential growth from the present level to a much higher projected level during that time. There also was a major requirements study, which was done by the Energy Sciences Network in the United States. And you can read all about that and the requirements set forward by several high-energy physics programs at the link which I posted there. There were 3 areas of particular concern for the LHC program: exceeding the capacity across oceans, not only the Atlantic, which is served by the Advanced North Atlantic Network Consortium, but also there is an ensemble of sites in a worldwide grid with 13 national centers and more than 170 so-called Tier 2 centers at universities and small laboratories. And the projected requirements at these campuses is having to support sustained groups of bursts of 400 gig per second, 400 gigabits a second, which corresponds to transferring a petabyte in a shift. Also, the major labs will require true terabit per second links. So we're working towards that, encouraging the facilities and the campuses to migrate in that way within the next few years, but also developing a system to deal with these challenges. So you can see an example of the traffic growth. This is on the upper left. You can see the STAR network, which connects the CERN site to the national so-called Tier 1 centers. And it also shows the traffic growth, which took place in the last year. Actually, as we'll see, we've now passed the period when the traffic temporarily decreased somewhat because of a COVID-19 pandemic. But in the last year, the overall traffic growth in and out of CERN grew by 68%. This is the worldwide LHC computing grid. the global monitoring, which is provided at that site, which I have listed. As I mentioned, it's a worldwide grid. And I broke up the traffic across this grid into time periods using the beginning of the last physics run. Actually, it's the middle of the last physics run as a baseline, and show that there was growth within a couple of years by a factor of 2.6 times, then a fall when COVID-19 took hold. But in the last 12 months, there's been the 3 times growth. So we've resumed this exponential growth. And the traffic is again above the pre-pandemic level. In terms of meeting the scale, part of the picture is to carry out certain exercises called data challenges. The first exercise was at the 10% level compared to the high luminosity LHC level. In October 2021, we exceeded more than 100 gigabytes a second for greater than a day. That could be supported on the present networks across the oceans and in the United States and Europe and Asia, but the 30% challenge scheduled for the fall of next year will be a real challenge. This just shows that the LHC will, in its second major phase, will have a major increase in the rate of the proton-proton interactions, what we call collisions, and also in the primary data taken per year from about 20 petabytes a year today to about 600 petabytes. This is for the single LHC experiment CMS alone. The Atlas requirements are similar and perhaps just a bit larger. Apart from the scale problem, the other challenge is complexity. A few years ago, the research and education networks got together and formed this virtual routing and forwarding fabric called LHC-1. First, it was for LHC, but now serves many other programs such as Bell, Nova, Auger, and so on. And Juno is a big experiment now being constructed in China. There are more than 62 domains here, and you can see just by looking at the diagram, which was generated by Bill Johnston, the former ESNet project manager, that this is a very complex system. And in fact, there are many domains, they're interconnected, sort of ad hoc. And the good news is that the world's research and education networks have mobilized to support these science programs. The not so good news is that this is really not an engineered system meant to manage and also deal with the constraints of the aggregate capacity of all these networks. So enter the Global Network Advancement Group. This was formed in 2019 with an overall mission to support global research and education using the technology, the infrastructures, and investments of the participants. And it brings together researchers, the National Education Network, global exchange points, regional networks, and other network providers to develop a common global infrastructure. Busong Cho tomorrow will talk to you more generally about the GNAG. In 2020, we formed the Data Intensive Sciences Working Group to deal directly with those challenges I mentioned, to meet the needs of those programs, but equally important to do it in a manner which is consistent and compatible with support for the needs, namely the traffic flows of the much larger academic and research community in the world at large. So we function as a forum for discussion, a framework for sharing tools, and we now have a development direction that I'll show you. And we've developed a persistent global testbed to which we welcome very much additional members, for example, the members of APONET, if they're not already members, to join us in this effort. There's a special focus of the group on workflows that integrate the network as a resource, comprehensive data management across multiple domains, automation, and infrastructures which are federated, which encompass networks, computing, and storage. There's another very important working group that I'll highlight called the Auto Goal Sense Working Group that deals with the deployment of virtual circuits, multi-domain circuits with bandwidth guarantees. These are the members. and also some of the member organizations. You can see there's a very wide range of research and education networks of projects and certain leading universities and laboratories. We meet weekly now, essentially every week, and everybody is welcome to join. So our top line message and the direction we've taken is, in order to meet the needs, we need to transition to a new dynamic and adaptive software-driven system which coordinates networks as a first-class resource along with computing and storage across multiple domains. As I mentioned, it needs to support the LHC and other programs and also accommodate other traffic and deal with something new, which is constraints in the overall available infrastructure. So from the systems point of view, we need to develop a global dynamic fabric that flexibly allocates, load balances, and conserves the available network resources. And it negotiates with site systems which have their own aims to accelerate the workflow of the groups of scientists and the programs. And as we'll see at the end, also an important element of this direction is the use of methods of machine learning, which are well adapted to deal with this problem and optimizing the system once the mechanisms are in place. There are a wide range of ongoing R&D projects, ones that deal with the formation of so-called data lakes to treat nearby sites as a unified site to simplify the problem, ones which have to do with the formation of intelligent data planes, and machine learning-based optimization projects. And I've listed some of them. I won't be able to explain every single one today because of the length of time, but you can be able to follow up, and I will be giving longer talks, which I'll make available to you. A key milestone, which is sort of at the foundation, is the integration of the results of this project called SENSE, which was led by ESNet and is now moving from R&D to deployment and moving towards production, to integrate that project, which is able to deploy virtual circuits across multiple domains, with the data management projects, the data management systems, namely FTS for data transfer and RUSIO for data management of the LHC program. And we're also dealing with, at once, in parallel lines of development, many of the worldwide moves towards a fully programmable ecosystem of networks and end systems. As many of you know, using P4, the P4 integrated network system, also source or segment-based routing like SRv6, and also particular operations platforms like the Open Science Grid, the National Research Platform, which is led by San Diego, and our global testbed, which I'll show you. Okay, so we made a lot of progress in the last couple of years. We're on the verge of persistent operation on our global testbed and being able to create this overlay layer 2 and 3 topology of virtual circuits. And at layer 3, we also are now using IPv6 and SRv6. We will, and actually SRv6 will come in the near future, to direct and manage flows on a shorter time scale. So there is two time scales, the one in which we deploy an overall network, which is not that dynamic. And then within that at layer 3, directing flows and groups of flows from sources to destination. We're also in the midst of the first migration, not only in demos at supercomputing conferences, but moving towards production, the first 400 gig elements. And we're seeing that at Starlight. We also have in LA and at Caltech and our SDN testbed. And SC22 will be a major set of demonstrations that I'll show you. Okay, so I'll mention other components. We're working with a Qualcomm Gradient Graph group. This was previously the Reservoir Labs company that developed this mathematical framework for identifying and dealing with congested links in a complex topology. We're also working with the forward-looking blueprint committees of the experiments to integrate network R&D and services in the workflow plans of the science programs. So in the longer term, we foresee a stateful user-defined stateful user-defined labels in flow groups, agile flow steering, and load balancing, enforcing compatibility with the aggregate of best effort flows on shared links, and using machine learning for modeling, prediction, and optimization. Okay, so this just lays out the fact that to meet the scale challenge, we're going through a series of cycles, a functionality challenge, which we're developing to develop the functionality we need in our system, then scaling up through our data challenges, and finally an end-to-end system challenge. And you can see at the bottom the sort of rough progression from 2021, 10% level, 30% level I mentioned for next year, then 60 and 100%. So as I mentioned, one of the foundational subsystems in our overall picture is Sense, the products of Sense, the project called SDN-enabled network for science at the exascale. That's where the acronym Sense came from. And there's an orchestrator, and then there are resource managers. There's a network residence resource manager, and there's a site resource manager, which was developed in my group. And the point is to be able to enable applications to make requests to the network, gain information, and negotiate between the orchestrator and the site resource managers in order to allocate bandwidth and with higher level services to manage the flows. So one thing that came up here, which is laid out here, I mentioned already some of the outcomes of the Sense project, developing mechanisms for an application workflow to obtain information about the network services and negotiate and interact with the network and negotiate performance parameters, discover what is the realistic performance metric, and match expectations to what is actually observed. A very important thing is the integration with these mainstream data management systems and tools of the experiments. So I mentioned FDS for data transfer, Rusio for data management, and XRD is a protocol for federated data access and distribution. One thing that's enabling us is the willingness of the Energy Sciences Network to support our plan, and will allow us to use up to something like 75% of the future link capacity for policy-driven dynamic provisioning and management by the time of the high luminosity LHC. So we're in the midst of an 18-month, 4-phase schedule to develop a plan, the real plan, through prototyping and tests to actually develop a development plan between now and then. And it's supposed to end by the end of 2022, when we'll actually have the multi-year plan in place. So this shows a picture of the Sense global testbed, which is growing. You can see many sites, and if you look carefully, you'll see sites in Europe. You'll see Jinan and US Internet 2 and ESNet. There are sites in Latin America. And also on the left, you can see there's the National Center for High Performance Computing in Taiwan, and Guam, Hawaii, and at the top, KAUST, coming to the US via Singeren. And also now we should update this plot to show some new links, also use of the JGN link to the US. So this is a global test bed, which is growing. This is a present status. We're starting to do exercises. One focus is the links across the Atlantic, because that's one of the first places which we expect to see congestion. There are 9 links across the Atlantic, and soon we expect an additional couple of links from a project called Bridges, which is coming online. But we need to learn how to share and flexibly use these links. One mechanism is to allow congested links to move traffic over to less congested links. You'll see a bit more towards the end of my talk about that. These programs launch jobs to be executed in large numbers. It could be anything from 1,000 to 20,000 jobs. Associated with those, we clearly don't want to manage every flow individually. We'll deal with flow groups and use not only priority, but also policy regarding the different groups. But every flow has to complete, and therefore we don't want to manage every flow, but in the end, ones that don't finish, we have to manage any flow. And like I said, it's equally important to understand how to have this coexist with all the best effort traffic of the larger academic and research community. Okay. So these are some of the goals. And this is one way where you can quickly see some of the things I said and the status. So we're well advanced in terms of deploying our global testbed with its layer 2 and 3 virtual circuits and integrated with these data management tools on the science program side, but also starting to do bottleneck structure analysis and act on that, and also to use the outcome of other research groups. Some of you may have heard the ALTO group, the application level traffic optimization group led by Yale, which is also working to integrate with those two tools for the LHC side, but for the other large experiment called Atlas, also working with P4 and pins. And we have wide deployment of the Géant Rare free router and also sites which are now running the software operating system Sonic. I mentioned we're starting to integrate 400 gig elements. We have a group in particular from Brazil called UFES, which has developed a new segment routed architecture, and we'll compare it to the industry direction, which is SRv6. We also have 5G applications. The interconnection of UCSD and NYU is being set up, and we'll use some of these tools also to manage the interconnection. We also have another project, which I won't be able to do more than mention, on a future network architecture on named data networking. Now, along with that worldwide testbed, one thing that has grown is a set of sites, starting with sites in the Géant network in Europe, but now spreading to other regions of the world, namely US, Latin America, and also Korea. We have a large number of sites which are running P4, and some are running Sonic. So there's a map at the top, which is sort of a live map and shows the active sites. There are 16, which I've counted here. And the next couple of months, we're going to add 9 more. So there'll be an increasing degree of intelligence which we're able to inject in deciding how to manage and distribute the traffic over this worldwide footprint. Now, I just want to say a few words about SC22 and SC21. Last year, the supercomputing is a big occasion to show things on a large scale. And so last year, we did have exercises both with the SENS project and many other projects. And what we show here is some of the 400 gig links that were set up at Starlight and between Starlight and the venue, which was in St. Louis. And also you see some links going to Internet 2 and then Pacific Wave, which is the West Coast of the United States towards the left. In SC22, we have this vast partnership, which I formed within the Data Intensive Sciences Working Group. And you could see all the logos here and all the group participants. All of these ideas are being embedded in a composable architecture. We have many lines of development going on in parallel, and then progressively doing some level of integration. Given the wide range of partners and the global extent, this is a general trajectory of development that works well. So the overall concept is to advance put the advances within a composable architecture of different subsystems, components, and interfaces among them. So for visibility, namely for pervasive monitoring, we have a number of tools I've listed here. See, I won't have time to really read them all out. For intelligence, we have NetPredict and Hecate, which are products of Mariam Kira, and I'll say more from LBNL and ESNet. And also I mentioned this gradient graph and other tools. For controllability, the SENS layer 2 and 3 virtual circuits, P4 and pins, SRv6 and Polka for source-based routing and stateful decisions at the ingress and egress of a segment. And different network OSs, the Jinan reo-free router is a very capable OS, both for full programmability, and there's also a different flavor of image, which is a full-fledged production image. And we're also working with Sonic. And then for orchestration within Sense, Kubernetes and the Kubernetes namespace, which will enable us to deal with different groups of flows and resources according to policy and priority and network state, etc. So I wanted to come a little bit.
Professor, we are running out of time. So
okay, so let me move ahead quickly. Let me just say, so I wanted to emphasize the group by Mariam Kiran and our partners on self-driving networks. What you see here is a self-driving network does adaptive routing with real-time data for routing decisions. It learns to avoid congestion, which means in many cases you can have a loss-free network, move towards greater utilization, and also do proactive fault repair. So she uses traffic classes, network monitoring data from many of the switch routers, and also a model of the topology to make intelligent decisions about network engineering. So she does both model-free studies to do path selection for large data transfers to achieve better load balancing, also for forwarding decisions across complex network topology, and a model-based study to predict network patterns with a tool that she calls NetPredict. So this shows the results of some of the things about NetPredict. In particular, the machine learning method that she's used, which is very effective, is dynamic diffusion convolutional recurrent neural networks. And you can look that up, and there's one of a number of interesting references. It's also been successful in spatiotemporal forecasting in other fields, in neuroscience, in climate, in real traffic flow of vehicles, smart grid logistics, and supply chain. And then her DeepRoot project uses deep reinforcement learning, which is therefore model-free, and looks at a number of optimizations of objective functions, whether you want to reduce packet loss or reduce the flow time, and we can add more stateful decisions. In the real case that we have with many classes of flows, we're going to be doing more stateful decisions, but having set up this mechanism, we're well positioned to do that. This just shows some of the improvements that she achieved in simulations of the Google B4 network and the Jinan network on different ways of carrying out the learning in order to minimize the delivery time. And you can see at the end, the multi-agent meta-learning technique was the best one. This is a simulation, which I guess, unless I make it full screen, if you look at these slides and make it in real presentation mode, you'll see it's dynamic, and it moves traffic from the red links, which are congested, to other links to achieve a better load balancing across the complex topology. This is actually the ESNet backbone that you're looking at. Coming towards the end. So also we're starting to look at wireless applications. We'll be doing this also at SC22. She has some of these small devices. There are even smaller ones without these long-range antennas, which can be used. And then after this, we're going to move forward also to mobile wireless networks. And she's also going to look at quantum network applications. There's a longer presentation. There's a link there you can follow. So that's it. So the top line message is, in order to meet the needs, we need to transition to a new dynamic and adaptive software driven system that can meet the needs while accommodating other traffic of the larger community. We have many components which are going into this system and a global test bed. The AutoGoal Sense technology is an important foundational element in this, but we're also looking into multiple advanced methods which are part of the worldwide migration to software-driven programmable networks. And so all of you, who work on AI machine learning for networks and the research and education networks in general are great partners in this. By satisfying these needs in this way, we also hope to bring a lot of value back to the research and education community, research and education network community in the way that these networks are operated and managed. Thank you.
Okay, thanks a lot for Professor Newman to share the experience. A lot of research work has been done. Due to time limitation, I think we can take one short question from the audience. So is there any questions?
Hello, I have a question. Could you give some advice on when we're using the deep reinforced learning to predict network patterns for the traffic engineering optimization?
Well, yes. So, I see Mariam's online. She can even better answer. But like I said, that particular approach of dynamic diffusion, recurrent neural networks, convolutional recurrent neural network, has been rather successful. So that's an area which Mariam, who again can speak if she'd like, has used successfully.
Yeah, Harvey is doing such a great job. So there is the prediction part, and which is also useful, and the deep reinforcement learning uses Q-learning technique. So basically it iterates through multiple paths and learns the best path for a given flow. And then over time, it can learn what the best strategies are. So there are a number of papers which we can send you. Me and Harvey also have a chapter on this, so we can send you more details for this.
Yeah. One thing I can say is reinforcement learning, is model-free. And unlike model-based approaches, if you decide on your metric, then you can know when you're doing better, obviously. But for our real case, with all these factors of all these groups competing and, things have priorities, and then also certain groups of flows approach deadlines, the decisions become very stateful, and it's a multi-objective problem with constraints. And the development of metrics itself is a very interesting research area.
Thank you for your suggestion.
Can I ask one question? Actually, your science network is very impressive. So some of that network is the SDN enabled network. Then do we have any plan to apply machine learning to the SDN enabled network or orchestration for
Yes.
networks?
So I think, as you see, we have many developments to do, to put mechanisms in place and to learn how to manage the traffic in a basic way. My answer is that once we put the mechanisms in place, and then we start to define metrics to try, they're going to be complex. And so then we need to apply machine learning to optimize according to that. But then when we do it, when you have a complex metric, there are other factors like, sentiment, or, maybe you've reached an optimum, but are there any aspects of what you're doing which are really far from optimum, or people actually object? For example, some of the work is not getting done, or who knows what. So then it's actually beyond machine learning, it's actually then a matter of game theory. Namely, humans are in the loop, and you have to try out certain metrics and then meet with the people and say, how are we doing? And they'll say, well, you're doing great here, but you're terrible over there. But this is a classic game theory problem.
Okay, thank you.
Okay, thanks again for Professor Newman to share.
You're welcome. I apologize for taking more time. It's a big subject.
Yeah, thanks a lot. Okay, so let's move to the next speaker. Due to the busy schedule, Professor JongWon cannot be here, so another speaker, Dr. Chu Sing, right, from the Southeast University, will give the next talk. The title will be Applying Deep Learning-Based Methods in Encrypted Traffic Analysis. So, Dr. Chu Sing?
Hello, could you hear me now?
Yes.
First, very thank you for inviting me here. Now, I'd like to share my screen to you so you can see the slides. Here, could you see the slides right now?
Yes. Yes.
Okay. So, dear disgusted chairman, scholars, ladies and gentlemen, first, good morning. I'm Xin Chu, a PhD student of JongWon, professor from School of Cyber Science and Engineering, Southeast University. Today, it's my great honor to share you the latest progress of applying deep learning-based methods in terms of encrypted traffic and authentication. Now, let's get started. Well, to begin with, my presentation will include these 3 5 parts shown in the catalog. Firstly, some background info about this research, and secondly, the definition of encrypted traffic identification. Next, about the academic deep learning progress in encrypted traffic identification. Typically, we unfold this topic a bit onto concrete problems in terms of website fingerprinting via CNN-based method and the app classification via RNN-based method. And after that, we need to conclude this topic in terms of 3 important points. Furthermore, the future research prospects are shown in the end. First, I will focus on the continued development of the encrypted traffic. Now you can see the statistics shown in these pictures below indicates that the proportion of encrypted traffic is continuously increasing, along with the rate of user awareness of privacy protection and data security. The traffic encryption is widely used in internet network communication. It has become an inevitable trait. However, network traffic encryption not only provides privacy and security to our users, but also brings challenges to network security supervision or the traffic management. Here also, considering the rapid advancement of our internet technology and network infrastructures, boundary bandwidth has exceeded TBPS level, you can see here, and the proportion of 100 Mbps fixed internet broadband access accounts is risen to you can see 86.8%, and internet traffic in the backbone network will be further increased in the future due to the development of 5G tech. As an update alternative version of TLS version 1.2, the TLS 1.3 encrypts all the handshake information, all the information after survey hello, making the current encrypted traffic analysis method based on plain text of handshake invalid. So at the same time, additional TLS 1.3 characteristics also generates the the concept drift for the classifiers trained on the traffic of version 1.2. So because of the concept drift, Therefore, research on encrypted traffic analysis should give more consideration to encrypted traffic on the new version, 1.3 of TLS protocol. Besides, the low latency of TLS version 1.3 enables it to be better applied in encrypted traffic service over the HTTPS protocol, which requires both high reliability and no latency. Namely, it will gradually replace 1.2 to become a new mainstream encrypted network communication protocol. So next, it comes to the definition of what is encrypted traffic identification. Well, in order to achieve fine network management and security, it's necessary to identify the metadata of encrypted network traffic. That is, the internet service content transmitted in the encrypted traffic load in terms of applications, the protocols, and the user behavior, or the QoE associated with the contents. You may further ask about internet service. Well, its core point refers to a specific and orthogonal artificial set of internet applications, which is domain-based and core-grained related to user behavior. Well, the traditional traffic analysis method relies on the DPI method to match the specific fields of the load in the plain text message. However, with the background of recent encrypted traffic we introduced before, the DPI cannot match the encrypted load contents. So it's very difficult to realize the fine-grained and real-time analysis by traditional methods. We need a row flow-based learning method. Well, here comes machine learning-based methods, which utilize the raw data or statics for modeling to identify those encrypted traffic. However, some limitations inevitably come up that, on the one hand, manual designed features which are used in machine learning depend on huge professional knowledge, which costs much human efforts. On the other hand, models are easy to fail because of, concept drift I mentioned before, so that they are needed to be updated in time, and new data simultaneously are required here. These disadvantages are solved when deep learning methods widely apply, as deep learning could extract the most essential and effective methods with end-to-end frameworks. Hence, we focus on concrete instance, that is, academic deep learning progress in encrypted traffic identification. First case is about website fingerprinting via CNN-based method. Here, initially, we need to know what is website fingerprinting. Website fingerprinting is representative for website homepage, which can reveal user privacy, such as online purchasing habits or video viewing interests. But why it's difficult? One point is that these web pages are on the same website, subsequently cause striking similarity to confuse these models. Another is about the huge data. Carrying out the curve that is hard to manually design the fingerprinting. And here in this story, CNN method is used to handle these problems. To begin with, we see the overview of CNN model. Here, we see traffic capture part, model input module, feature extraction and classification module. We will specifically discuss them in the later chapters. Let's review the structures. First, we use intercepted flow sequence as input. We determine a length threshold n here. If a sequence length exceeds the threshold, we intercept the first n elements from the original input. In our model, there are 5 blocks for future extraction as shown in figure below. In the first 4 blocks, there are 2 consecutive convolutional layers before the pooling layer, and in the last block, there are 3 consecutive convolutional layers without pooling layer. The number of filters in the last convolutional layer is equal to the number of, namely our website labels. After each convolutional layer, there's a batch norm initial for BN layer that accelerates the training of neural networks. Here, when it comes to the activation function, nonlinear ReLU in each convolutional layer are used. This will greatly increase the nonlinear of neural networks and improves the expression ability of neural networks. This method replaces traditional fully connected layer with GAP, global average pooling layer, which significantly reduce the number of parameters, thus greatly improving training speed and reducing the risk of overfitting. It accepts the output of the last convolutional layer and averages each future map in the time dimension as shown in the formula here. Even with the basic model, some optimization ways are required. It's essentially a multi-classification task. Namely, we use cross-entropy loss function to calculate the loss between the predict values and the ground truth. We use a Dama optimizer to minimize the loss during training. There's a risk of overfitting in the training process of CNN modules. In this part, we add a dropout layer at the end of each block. In the forward propagation, the dropout will make the neurons stop working with a certain probability, so that the module will not rely on some local features so too much. Besides, in order to reduce the complexity of the model, we introduce L2 regularization here, which tends to make all parameters smaller to constrain, the complexity of this model. Next, we make 2 key observations from the results. Here, in local attack scenario, the results demonstrates that the downlink burst sequence, not the uplink, used in this method, as well as the CNN-based classifier proposed here, can extract discriminative features in similar web pages. That's great. And in the remote attack scenario, this burnets can also work well, whereas the accuracy of other methods drops dramatically compared with the results in local cases. It also confirms that the remote attack scenario imposes more challenges on WF methods, as you need directional traffic leaks less information. That's important. While in the open world experiments, from the table, we can observe that Barnett achieve 99% precision and recall simultaneously on both data sets, which is better than other methods. Moreover, fully connected methods tends to predict all instances as monitored. So its recall on both datasets approach just 100, was the precision is relatively low. Also, considering the time cost, results in table showing that models which leverage CNN take longer time compared with the traditional machine learning based methods. Although Barnett has deeper convolutional layers, it needs less training time than other methods because it does not include fully connected layer and thus significantly reduce the amount of parameters for training. The second step follows another specific issue called app classification via ARM-based method. Here, app classification is simple to understand to everyone, but what's important here, because encrypted traffic races sharply whereas traditional rule-based method fails. More attention from both individual and public are paid to communication security. The difficulties can be summarized in 2 points. One is about randomized contents, resulting no obvious features. Another is about piecewise design restriction, as there is no guarantee to global optimum. So here, this ARM-based method is a hierarchical model and consists of 7 layers as shown in the figure below. It enjoys the advantages of both supervised and unsupervised learning. In the following of this section, we will present this structure in some detailed ways. This method just input raw flows without any operation. For future learning, it uses embedding and the association of, here, encoder and decoder and the dense layer also. In this part of classification, softmax and loss function are introduced. It should be noticed that the ARM module, namely one of the most popular neural networks, is laterally suitable for sequence, as ARM can remember the past info from the previous state. It also infers the current state based on the previous state and the current input. The specific formula is shown here. The main weak point of the basic RN is namely vanishing gradient problem, which namely cannot retain the long-term info. The advancement of this GRU series adds the gating mechanism to control the info transformation between the hidden states and the trick of the states of the input sequence without using separate memory cells. The architecture of GRU is shown in the picture, here, which including reset gate, hidden gate, and update one. Here we introduce the auto-encoder detail. Auto-encoder is one of the key points of this structure. It compresses the raw input and learns features that can represent the main points of the raw input under, the reconstruction mechanism. The formula here seems complex, but in a word, the by GRU is adopted to incorporate contextual info of the embedding sequence by summarizing sequential info from the both directions to further improve the representation of the encoder. The multi-layer bi-GRUs are staked in the model. The low-level expressions learn the local features, while the high ones are composed of combinations of low-level expressions to obtain the global features. These features may be helpful for our classification problem. So let's take a brief look at the similar optimization compared with the last part. The loss function of this model consists of two parts, namely classification loss and the reconstruction loss, with alpha as the trade-off factor. The balance of these two losses can learn distinguishing features from global perspective, which are beneficial for the final task. As it comes to overfitting problem, two-layer SLU activation can use to compress high-dimensional data, and this trick can increase the nonlinear features. Well, next part, we move on to conclude our topic in terms of 3 key points. Here, firstly, we need to extract the length-sensitive flow sequence features, which is naturally most important one, I think, such as intercepted flow sequence and just raw flows shown in the slides before, Second key issue is about creating end-to-end neural network models. Researchers should consider not only the compatibility between the data and their models, but also the integrity of models to achieve global satisfaction. Last but not least, don't forget to optimize your models in both loss function and overfitting procedures, etc. Lastly, in the future, some research prospects are introduced here for us to consider and also study further. First, in the perspective of future extraction, creating more representative features is effective approach. Some studies in this way are popular, like graph-based features and the small sample learning. It is so popular now. Also, we could take a look at the model improving. That is to utilize more suitable and advanced models such as the GNN model and transformer. Lastly, to design more realistic elements in your experiments is also necessary. So try your best to handle scenario optimization. Well, that's all for my presentation. I'd like to say thank you for your listening. Wish you enjoy this topic and have a good day.
Okay, thanks a lot for Dr. Chu. So any questions or comments from the audience?
Yes, hello, I have a question.
Hello.
Yes, my name is Javier Diaz. I am a PhD student in Jeju National University. Yes, I find the presentation quite interesting. I just want to just clarify some subjects. I guess this is a follow-up on a research project that has been continuously done, correct? From the previous years, I think I have seen like a similar research in this classification of encrypted traffic in this working group. So there are like 2 points that I were mentioning here about the performance of the classification itself and the method of classification that is being done. I mean, I know that the preference here is the use of deep learning because of how like we can apply, right? Like these algorithms, these RNN, in order to effectively classify the encrypted traffic. But as far as I understand, then we are using a data set that is labeled by the signature of the web browser or the actual sources, right, of the traffic. Am I correct?
Okay, so I think, namely, I'd like to say what's here, the AI-driven vehicles is not the most important thing, but the networking itself. So the feature extraction of the raw data, the flows, and creating more representative features is more effective and important. But the advancement of the models is about others. It is about others. So I think with the development of these models, the results or the performance will become better. But what's the nature? What's the nature, and what is most important about the feature itself is more important for us to study. That's my point. Thanks.
Yes. Is there like some, besides this, further further research that was presented in the last slide? Is there some other consideration regarding the advancements also in the encryption part? Because we are thinking about like this security point of view of the networks, correct? So technology also evolves, so the security mechanisms will also evolve. So this may also impact in the actual detection or classification mechanisms, but because the features may change depending of the encryption algorithms or the encryption methods that are being done. If there is a different standard that may be created or that can be applied, or if we move completely to encrypted like traffic and we are just working in a black box itself, correct? So I guess this thing also can impact, right, these detection mechanisms. Am I right?
Yes, here I think some specific details, the tags about the solving of the raw data is more engineering. Sorry about that. I'm not the engineer here, but maybe the raw data could also achieve the good performance as well. Some specific or algorithms, like the dynamic routing and other etc. algorithms may be used here. So it's about specific engineering points here. Maybe we need to focus on that further. Thanks.
Yes. Thank you very much.
Okay, due to time limitation, thanks again for Dr. Chiu. Let's move to the next speaker, Woo Sin-ju from KT. The title will be the Korean Integrated Data Lake Portal Advancement. So welcome, Professor.
Thank you. Let me share my presentation. Just wait a minute.
Sure.
Can you see well?
Yes.
Okay, let me start.
Yes, you can start. Thank you.
Okay. Thank you, Chairman. Let me introduce myself for a moment. I am working for KT. My name is Sung-ju. I'm in charge of performing tasks in the KT Enterprise Division. Nice to meet you. Now, let's make my prepared presentations. First, before presenting, I would like to explain the meaning of KOREN, K-O-R-E-N. The abbreviation of KOREN is explained as follows. KOREN stands for Korea Advanced Research Network. Now, let me start my presentations. Today, the title of my presentation is KOREN Integrated Data Lake Portal Advancement. Now, next page. The purpose of this study is to monitor the traffic of collected data through the integrated data lake management portal and to build a big data cluster for storing and managing the collected data. For this purpose, optical signal strength data, traffic data by use organization, Korean International Network ELK traffic data, and S-flow data are collected. The manager can check the data collection status for each item, and it is possible to visually analyze whether the data collection is progressing normally. By applying various statistical functions for the collected data, it is possible to check input-output traffic informations in graphs and tablets. Supports external use for research purpose to download data through the AI data set with disclosure functions. And next page. The table of contents to be announced today is as follows. The chapter 1 was developed and complete in 2021. Chapter 2 is about the technology used during development in 2021. Chapter 3 is under development in 2022 and we will be complete by the end of this year. This slide shows integrated data lake platform architecture diagram. The integrated data lake consists of an admin page, dashboard, statistics, and AI data set disclosure screen. Administrator can access the full screen and external use can access only the AI dataset disclosure screen. And next page. This screen is the architectures of integrated data lake system. Collect raw data from the AI NMS system to distribute and store data through an integrated data lake. It provides pre-processing operations and data visualizations functions for data visualization and statistics, and AI data set disclosure functions through an integrated data lake management portal. And the next page. This following screen is flow architecture of AI dataset disclosure functions provided by integrated data lake management portal. And the AI data sets collected by the AI NMS system is distributed and stored through the integrated data lake system. It provides access right control and usage history management for each user and data set through the dataset disclosure function API. And next page. This page visualized the size of the raw data collected from the AI NMS system. These graphs display the collection status of core raw data. Example, optical signal strength data, international network traffic data by user organizations, S-flow data. collected through the integrated data lake management portal in the real time and visualize it as a graph. And if it is not normally collected, no data is displayed and alarm mail is sent to registered administrator's email through the alert function. Next. This screen visualizes the data collected by the integrated data lake system by calculating statistics on daily basis through pre-processing. In the case of the full screen, the statistic of optical signal strength data, international traffic data, and organization data, ASPRO data. And next. This screen is statistical screen useful for Korean administrator of optical signal strength data. You can select the time range for statistics through the field selections window at the top. The graph is graphic visualization of RX and TX value of optical signal strength data by IP classifications and ports. For the graph, it is graph for over range of months, and since the data is collected every 15 minutes, 1 point is the average value over the range of 50 minutes. Next page. This screen is a traffic data by user organizations screen. You can select the time range for statistic through the various selection window at the top. The top table is statistical table of the maximum, minimum, average, maximum, minimum uses rates of in and out traffic by user organizations. It is screen the visualize the top of 6 traffic value of input traffic, output traffic, input average traffic, and output average traffic, and tables and bar graph. Next. This page, the Korean international network traffic screen data. You can select time range, international network traffic data based on total in-out traffic value by user organizations, country IP, IP ports, applications, ports, etc. It is screen visualized as a bar graph and pipe graph in descending order. And next, ASPRO screen. You can select the time range for statistics through the various selection window at the top. The top table shows the total number of records, traffic capacity, and packet count of ASPRO data. In case of pipe graph on the left below, the number of records, traffic capacity, and packet count are shown and descending orders based on origin. And the case of the bar graph in the middle, the origin and destinations. The right side is the destinations. Next page. The data set disclosure screen, meanings it informs the details information of data set publicly by the administrator. The list of download detail files and the data schema information of the file. When you click the download buttons, the data file is downloaded. And then next, our projects, we use variable scale technology. So I like to introduce the scale for our project. This page is the integrated data lake software architectures classified by roles. It is divided into collect, message queue, MapReduce, sidecar, Presto, HDFS, monitor, AI data set download API. A description of each roles, it is the same as what you see on the screen. And message queue, MapReduce, Presto, and HDFS are clustered with 3 servers. And the case of AI real-time interference is performing through a real-time AI model. I've marked the key parts of the data lake with a red scale. And next page. This page is a Spark overview. In the case of Spark, this is software used in the role part of the MapReduce. There are parts in the core and our projects that require real-time pre-processing and the task for require statistical calculations. Spark was used to use the in-memory-based high-speed processing functions. Next. This page is an overview of Hadoop. Koreans use the Hadoop because we had the task of storing all the data collected from the current project. Data reliability and immutability is guaranteed through the Hadoop's HDFS. Scalability is guaranteed, increasing the storage capacity as you add servers to your Hadoop clusters. In addition, transparency is guaranteed, making it convenient for the administrator to manage data. In the case of Hadoop's distributed operations, that is MapReduce, it is not used directly because it uses Spark instead. Next page. HDFS overview page. This part is additionally explanations to explain on the previous page. So let me skip this page. Hadoop cluster overview page. Hadoop cluster is divided into the master names name node and the slave names data node. And it's guaranteed the reliability of data by replicating the set number of n when stores data. So HDFS is also transparent and can be used as a single file systems. We built Hadoop cluster in the current project and consists of 1 names node and 2 date node, and the number of replications is set to 2. And next. Presto overview page. In the case of Presto, it is other distributed SQL query engines developed by Facebook. It is also possible to search like GeneralDB. In the current project, in the case of project, Presto was used because it was possible to query data at a high speed and using distributed computing techniques through loading, calling, and clustering of data in Hadoops. In the case of Presto, it can be set at about 300 petabytes of data on Facebook are viewed daily and used for work, as you know well. Yes, next page. As you can see, the developer plan for 2022 is planning to upgrade to a total of 5 advanced functions and the total of 4 new functions. Detailed explanations will be given on the next page. This page is the structure of 2022 projects structures. And the integrated data lake, use history management, and the Q&A screen are additionally configured on the admin page and dashboard, statistic, and AI data download screen, etc. Visualization screen for newly collection data is additionally configured on the dashboard screen. And next page. We will be announced the detail of 22 developed plan based on the integrated data lake management portals developed in 22. So we plan to enhance the visual level to maximize working efficiency and improve the ease of use for administrator and our user. To this end, we want to expand the number of collect data and administrator can check on one screen by checking the data newly collected in 22. On the dashboard screen, the pre-processing and adding visualization informations through graphs. Next page. And the previously developed number registration screen. We can register for memberships for after entering ID, password, name, mobile phone numbers, affiliations. To this end, we would like to provide a separate management and statistical information service to a number of the Korean user organizations by adding a window to select whether or not to use the Korean organizations when signing up for membership. On this admin page, we plan to improve the visual level so that unauthorized and approved user account information can be managed efficiently. To this end, we want to make it possible to research for user, check our information, change permissions in user list, and in the approval waiting list, we want to make it possible to grant user rights by approving unapproving users. Next page. On the AI data set public screen, we plan to advance the visuals so that administrator can enter detailed information for each file and manage whether to disclose or not disclose each file. To this end, we want to display information on the file list corresponding to each type of failure and enable movements through scrolling when the list is out of the areas due to the large number of lists. And the previously developed statistical screen, only administrator was able to provide information service. But we plan to advance the visuals so that Korean user organizations can also provide statistical information service. So to this end, we want to make it possible for users of our user organization to check the statistical information about their company. So in addition, by adding newly collected data in 2022, we plan to expand statistical information by type that manager can check. Next page. new developments in Print to enable administrator to manage usage history, such as usage history by user, number of download by data. To this end, we want to make it possible to check information such as a number of login, number of data download for user in the usage history for each user. And in the number of download per data, we want to make it possible to check information such as the number of download per data item. And final phase, we want to develop a new Q&A screen for feedback space between administrator and the users. To this end, when user of our user organizations use the statistics and AI data set disclosure functions, or general user use the AI data set disclosure function also, we want to develop the Q&A screen where the administrator can answer questions about when they ask question in the Q&A first. And thank you for hearing my presentations. Okay.
Okay, thanks a lot. So any question or comments from the audience?
Yes, I am Walid from Jeju National University. I want to ask a question. This explanation is very good about the presentation of the data, how data can be visualized to the status of the network. My question is that which type of agents are deployed into network to collect the data? This is the first question. And the second question is that in the diagram on the slide number 14, you have a different components of the monitoring architecture. Here you have used the InfluxDB, you have used the MySQL, and you have used that Hadoop. Why there is a need of multiple databases if you can store the data in a single database?
Thank you for question about me. Yes. We collect data from AI animate systems.
Okay.
AI animate systems, we build systems also current projects complete. And then the next question is maybe you want to know SQL or another DB, another skill. So
yes.
So we use the big data, the file system, file technologies. So I introduced to you. Wait a minute.
Okay.
Yeah. Big data skills is we use the Hadoops or Spark or HDFS and Presto and another skills we use. Well, anyways, it's difficult how to understand. So please email the exactly contents of your questions.
Okay.
I will try to organize it well and give you answer. Okay.
Okay. Thank you. Thank you.
Thank you very much.
Okay, thanks a lot. Since we are quite late for the schedule, so let's move to the next speaker. Let's welcome the Pedro Martinez Julia and Red Cafu from the NIST to give a talk on adaptation of NFV systems with the autonomic research control architecture. Okay, let's welcome.
Yeah, thank you very much. This is Ved Kafle speaking. Can you hear me?
Yes. Since we are quite late for schedule, so please.
Oh yeah, This is the,
sorry.
Time-wise, I am at the end of my presentation, but how much time I can take?
Less than 20 minutes.
Less than 20 minutes. Okay, I'll try my best. So can I share my screen?
I don't think so. So Professor Wu, can you stop the screen sharing?
Okay, I'm trying to share.
Okay.
Can you see it?
Yes.
Okay, then I'm making it full screen. Yeah, thank you very much for giving this opportunity to present our research work. It's actually research on resource management, network resource management by using AI or machine learning techniques. I am Beth Kafle from NICT, and my co-author is also from NICT, Pedro Martinez Julia. So for this research, as you know, the network system is going to be based on virtualization platform. So resource management has become easier in the sense we have the tools to manage resource dynamically. And but the system is also getting complex because the network functions are going to be virtual network functions or container network functions. So there are a lot of places where network function will be kept, and we have to monitor them. And in order to monitor them, the traditional way of like collecting data and checking with respect to some threshold would not be enough. So what we need some sort of autonomous resource management scheme, and for that purpose we have proposed the autonomic resource network architecture. So we called ARCA, and today I'm going to introduce you ARCA and related research. And this also shows the motivation why we need dynamic resource management, or why we need regular adjustment of resources. So this slide shows one very clear example. Let's say if we have allocated some fixed amount of resource shown by this green shadow, then what happens? And these red bars are showing the actual resource usage or demand. So as you can see, the resource usage or demands are very fluctuating, but the allocation is static. So in this way, when the resources are not being used, those resources are being wasted. And when we need more resources, there are no resources. So network service quality would not be good enough because of the shortage of resources. So for that purpose, in order to address the resource demand in dynamic environment, we need elastic resource adaptation or management. For this purpose, we have this ARCA solution. What it does, it is estimating the resource demand based on performance measurement, as well as detection of some events which are outside the boundary of the network system. So these events may be some social events. Let's say if some disaster occurs or something, some event is going to happen, then the network usage would increase. Network traffic may increase because of the users' activities. So if for that purpose, we need to adjust the resource dynamically. And in order to adjust the resource, we have to make the decision. So in the decision system, we have 4 components: collector, analyzer, decider, and enforcer. So collector is just collecting information, measurement data from the network, resource utilization or the network performance metrics. And analyzer is analyzing the data to find a situation, to understand what is actually happening in the network from the collected information. And then decider is finding some action needed to resolve the situation, and enforcer will be implementing the action. So next slide is showing you the diagram. So here we have collector, which is collecting information from the resource utilization performance metrics. It can be from controller or some things, some sensors. So we collect information. And here then we have the analyzer. In this analyzer, we use various AI or machine learning techniques. And then again, we have the decider, which is again preparing some sort of knowledge base and performing reasoning. And then we have the enforcer. This is actually orchestrating the decision or action for the resource control. And the operation is taking place in the closed loop. So this is what we have shown in various call out box. And we have the administrator, which is providing some sort of like the threshold or the upper and lower limits of the resources that can be assigned, or we can also provide some sort of QoS requirements, like how much latency or how much disturbance or the packet loss we can tolerate. Those values will be provided by the administrators, and then action will be carried out here. And the operation is closed loop. Sorry, operation is closed loop means after performing the action, we are again collecting the feedback and we are checking how much was the accurate action we carried out. In this way, we can learn. So for learning, we can use various approaches. We do some prediction of the user behavior, and we also correct mistaken prediction based on the closed loop operation that I mentioned to you. And for the learning and this reasoning, we have been using case-based reasoning. And this platform that we have proposed has been applied to the HC NFB Mano architecture, and our system ARCA is being used inside the NFB management and orchestration block, and we use various interfaces for communicating with the concerned entities. For example, for the resource management, we use this virtualized infrastructure manager Vim API, and for the analyzer and decider, we use this OR VNF management, and for giving statements for the threshold, we are using this OSS, BSS, and the NFBO interfaces. So this is the architecture outline, and based on that implementation, what we have observed or what we have investigated is written here. We investigate the feasibility of ARCA to improve current approaches, which are based on threshold approaches. As I mentioned earlier, current approaches are mostly threshold approaches. We design a particular algorithm to implement the analysis and decision using case-based reasoning methodology. We evaluated ARCA by using data set obtained from a scenario representing the real network. We obtained this from Google data set. And then we compare the amount of resources allocated by ARCA and the other approaches, related approaches. And we measured these metrics: total system over allocation and change of requests sent to the underlying controller. This is how frequently we have to control the network, where update the network. And we also measure the packet drop rates. In this case, with these three metrics, we are trying to capture the cost of the network operation, which is the resource over allocation. And we are also observing the overload of the network management and control, because how frequently we need to change the network configuration. And then we are also measuring the QoS in terms of packet drop rates. And for this purpose, we have one algorithm shown here. It's long, so I'm not going to repeat it. It's in 3 pages. And next, I'm going to give you the evaluation information. So in this case, what we have done, we have collected data from this Google cluster data. And from this data, we have basically focused on 2 variables. One is the severity of the event. So we can derive from the data about the severity of event, means how urgent or how important the event is to address by the resource allocation, and also the load of the system. So these 2 variables are extracted from the data. Actually, they are computed from the data, and we have represented them in terms of the percentage, like severity percentage and the load percentage, and their fluctuation is like this. And then from the load, we found that there is some potential correlation to the time of the day that can be learned, and it is not generally casual to event severity, but event severity, there is some frequency, but it's not time of the day. This is from the observation of the data. And next is the performance result. As I mentioned earlier, we have this total resource over allocation, and this is the frequency of the resource update and the packet drop rates. We have represented these results in terms of CDF. So from here, the threshold based is shown by the blue line, and the other our proposals are shown by the other like slightly red or green lines. And from here we can observe that this threshold based is requiring more resource over allocation, and the CBR based approach we have proposed. We set the different thresholds, threshold. This is how much overload, how much load in the resource is tolerable. Let's say 70%, 80%, 90%. So we can adjust the tolerable limits of the overload, and then we evaluated the these three metrics. And from the evaluation, we found that the over allocation, we can, with the threshold, we have a lot of over allocation, almost 85% of time, but ARCA is able to allocate between 2 and 3 servers, means it's reducing the over allocation by 50% from this graph. And from the other graph, we can observe that more than 98% of the time, ARCA didn't request a change to the infrastructure. In contrast, these threshold-based approaches are requesting like 6% more. Similarly, when we saw this packet drop rate, in the beginning, they proposed the system looks like it has more packet drop rate, but this is after a while it is resolved, and they are getting better than the traditional blue line. So in that way, we measured some preliminary performance evaluation, and then as you gave me only 15 minutes to, I'm trying to come to the conclusion. We have designed and implemented ARCA to adapt the amount of resource allocated to NFV, Network Function Virtualization System, and to meet their demands. We demonstrated that our proposal is able to improve the performance of the managed network. And this work is still ongoing. In the future, we will improve ARCA by exploiting additional methods of network intelligence. We have been applying various machine learning methods like support vector correlation and deep learnings. And at the same time, we have been involving semantics in the decision to get explanation of the decision. And then using given explanation and semantics as the source of reasoning, we will be resolving or prevent some complex situation and improve the performance. Thank you.
Can I ask a question?
Yes, please.
I am Mir Mohammad Suleiman Sarwar from Jeju National University Network Convergence Lab. My question is regarding the architecture of the ARCA model. You mentioned that the ARCA has been aligned with the NFV Mano. So my question is that can ARCA model be aligned with other standard models or architectures as well, such as the ITUT model for the machine learning in networks, and the, for example, 3GPP proposed the NWDAF as a component that could do the analyzing, the machine learning. So in your model of the ARCA, the collector, analyzer, decider, and encoder, the analyzer is probably analyzing the data, such as the in the 3GPP, NWDAF contains a machine learning model that analyzes the networks, collects the network data, and then analyzes data. So my question is that can these other models also be aligned with the ARCA model, such as you have aligned it with the NFV model? Thank you.
Yes, sure. Thank you. Thank you for the question. Yeah, that is the objective of this model. That's why we have developed these components in the form of the microservices. So they can be like accommodated or embedded with the various network components in a distributed manner, not in the monolithic manner. That is why, let's say, collector can be embedded. If you are talking about ITUT machine learning model, this can be the data collector of the machine learning, and this would be the network function, virtualized network infrastructure. So in that way, and this can be the analyzer, can be the pipeline, machine learning model pipeline, because this may analyze the data to make some sort of like regression analysis, and that regression would be provided to the reasoning place to understand about the real cause of the problem, or real like the point that is requiring resource adjustment. So such functions can be like accommodated with other architecture framework. And the reason we used this NFV Mano platform is because it can be easily integrated with the OpenStack, this virtual infrastructure management platform. And we have developed our system in OpenStack. That's why we used this framework, because it can be easily integrated. So, and I have shown this architecture here. Thank you.
Thank you. Thank you so much.
Can I ask a simple question? As far as I know, Japan has several national research networks. Do you have any plan to apply this kind of architecture to your research network?
Yeah, we have a plan. Actually, NICT is managing Japan's Research and Experiment Network, JGN. And we also have some cloud infrastructure as the research facility. The current, this evaluation was from our local testbed network that we developed in our lab, but it can be also be integrated with the large scale testbed network. And that's in our plan. Maybe in few years we will be transporting to the testbed.
Your network is nationwidely apply the SDN enabled network.
Yeah, that part I am not. Maybe, of course, it is. It's supporting SDN features, so it's has been equipped with those management facility. And because I'm not belonging to that research site, so I may not provide. I may not be able to provide you the exact information. But of course, yes, we can borrow some slice of the network and then perform the research.
And I think the Mano architecture should be applied to the physical networks, actual physical network of your research network. And I think this mechanism could be very effective for your research network. I hope your case study can be presented in the next our working group sessions.
Yeah, thank you very much.
Thank you.
Okay, thank you very much. Okay, it's great that you can control the time, and sorry for a bit late for the schedule. Professor Song, would you like to give a closing comments for this section?
Actually, your session chair, anyway, then, thank you for your presentation of all speakers. I hope it would be good for all attendees. Then we can continue our next session from noon. Then I hope all of attendees can continuously attend the second session and have a good discussion. Thank you very much.
Okay, thanks a lot for attending this section. So this is the end for our section. Hope we can meet in the future. Okay, thank you.
Thank you.
Thank you. Bye-bye.
Bye.
Okay, so I am Hiroki Kashiwazaki from NICT in Japan, and I will work as the chair of the second session. And this is the second session of the AI-driven network working group. So, okay, so the first presentation is intelligent network traffic forecasting in SDN and load threshold identification in wireless networks by Su, Satish Kumar Parmar, Pam Wei Sai, Ariska Christian, and JongWon. The presenter is, I guess, Su.
Hello, everyone. My name is Satish Kumar. So I will be the one presenting for the intelligent traffic forecasting in SDN from
Okay. So would you please share your slides?
Yeah, I will be sharing my screen now.
Okay. Oh, I can see it. Oh, please start the presentation.
Yeah. So everyone can see my screen?
Yeah.
Yeah, okay. So good morning to everyone. So my name is Satish Kumar from Malaysia. So today I will be going to present our research work, which is intelligent network traffic forecasting in SDN and also load threshold identification in wireless networks. So actually, this report is going to be explain our preliminary work done in our lab, which is divided into two different sections. So the first one will be intelligent network traffic forecasting in SDN. So the function of this first section is we want to perform the traffic forecasting by analyzing some of the metrics that can be retrieved from our SDN testbed or the network to do the traffic forecasting. At the same time, we want to reduce the traffic congestion. So the second part will be threshold identification in wireless networks. For this one, we will be identifying the suitable times where all the access points are at a capacity to perform load balancing between them by having a focus on mainly educational network deployments. So let me begin with the intelligent network traffic forecasting in SDN. So by moving into an overview of traffic engineering in SDN, currently there are multiple methods and techniques being available to actually perform the traffic engineering in SDN. So some of them include where we can make use of the metrics that we can collect from our network, such as the delay, jitter, packet loss, and etc. to measure the traffic performance before we can move the traffic forwarding. Other than that, we can also make use of the adaptive routing, where we can change the path cost by modifying it whenever the loads in a specific path undergo some changes. And we can also we can also make use of best path and a backup path calculation to do the traffic forwarding. Other than that, we can also distribute the traffic among multiple paths based on specific characteristics such as per flow or per packet basis. So the current status of traffic engineering in SDN. So when we want to briefly see the current status of traffic engineering, so most of the current traffic engineering technique proposed and being developed is using the measured traffic, which only reduce the observed congestion in the network and not the future congestion. But an improvement can be actually made to those techniques is by predicting the traffic changes, which enables the SDN controller to actually calculate routes by considering the future traffic demand. In this way, we can make the SDN controller to predict traffic variation in our network, then identify the routes that can actually fit the forecasted traffic without causing any congestion to the future and the current traffic that is flowing in our network. So this is our overall proposed solution of the mechanism that we are currently being developed. So there, as you can see, there are few mechanisms has been developing in side by side, which everything will be worked together to make the traffic forwarding or the traffic engineering mechanism to be successful. So primarily, I will be focusing on a traffic prediction, which is the primary module, which will be used by all the other modules. So when we want to do a traffic forecasting in our SDN network, the first thing we want to consider is we want to select a model which is best suitable for our scenario. So what we made is we made a few comparisons by considering few other multiple models for its consistency in the accuracy and also the resource that it can consume for the calculation. So some of it include the ARMA, the ARIMA, the moving average, the RNN-based LSTM, single, double, and triple exponential smoothing. So among all of the model, we finally we came to a conclusion to make use of a triple exponential smoothing, also known as the Holt-Winters algorithm. So this is because it is having a few advantages that are not present in other models. So mainly it can forecast an typical value, or also known as the average, and a trend in our traffic variation, and also a seasonality. Seasonality is like a repeating pattern over a period of time that can be set by our user. So it also can give more significance to the recent observation. So to make the accuracy to be much more improved. And it also can identify some traffic patterns and also trend after a fixed number of iteration. So the iteration is purely customizable by the user, where we can set according to a number of days, weeks, months, or even years. And it also suitable for a short and long-term forecasting, as all the parameters are customizable and set by the user. So this is some of the result of our prediction made in our lab. So at first we tried to fix all the parameter as a constant value. And then we tried to insert our training data set for a period of 1 year and make the prediction for 3 years. So by having a fixed parameter, we can get a mean square error of 41.69. And also we can see the graph in the picture, but it can able to predict the traffic, but not as accurate as compared to the original data. So, and then we try to further improve its mean square error by adjusting the training period by dividing into multiple data sets. We divided the 1 year data set into multiple sections and then made the prediction. So in this way, we can able to reduce the error to be 36.22. And then we also made advantage of the other parameters that is available for us to set. So that is the alpha, beta, and gamma. We also try to manipulate each of the variables. So in this way, we can able to reduce the mean square error much better and able to predict the data much more for its accuracy. We also further let the algorithm itself to decide the better parameter, the alpha, beta, and gamma, so it can improve itself to select the parameters which can able to produce or give us much more mean square error with the lowest value. Lowest mean square error actually lead to a much more accurate data prediction. So that we can see in the image that the accuracy has been improved well compared to our previous value being used. So even though we are able to do the traffic forecasting, there is a situation where we will be miss out some of the metric that we are collecting from our SDN network. So at that moment, there is a mechanism is needed to actually, we want to estimate the value of the missing metric that we are unable to obtain from our SDN network or the metric collector. So here we have implemented the exponential moving average that can intelligently estimate the value that have been missing or that are not able to obtain from our collector. So in this way, we can further minimize the overall surface curvature, because even a single metric that we are able to obtain can cause a reduced accuracy in the traffic forecasting by the Hot-Winters algorithm. So by using the EMA, we can further reduce the accuracy due to a failure when we want to collect the link metrics. So how it is done is it will place a more significance or a weight to the most recent data points. So in this way, it can able to predict much more for its higher accuracy. So this is the algorithm or the formula for the EMA as shown in the diagram below. So this is the prediction result using the EMA. From the first column, we can see that's the original data. And then we try to remove some of the original data in the second column. And then we try to use multiple algorithms as well in this situation, such as the linear, spline, prior, next, SMA, WMA, and also the EMA. So among all the algorithms, we can see that actually EMA is the one can produce a much more better outcome when we try to compare with the original data that have been removed by us. So this is the graph for the previous table. So here we can see much more clearly that the EMA can actually give us a much more better prediction in the metrics that have been unable to obtain by us from our SDN. So the future direction will be, we want to further improve the traffic prediction algorithm to actually optimize the parameters for better accuracy, even though it is able to do it by itself. But we also have to make other parameters to be chosen and at suitable condition. We also want to inherit the predict optimal traffic paths and future traffic demands in process for other models, such as the path calculation. So we will further integrate this traffic prediction to reroute the traffic in our SDN network before any congestion situation is actually can happen in our network. So that's all from my presentation. So my friend will further explain about the load threshold identification in wireless network.
Okay,
so
audio, YouTuber?
So
Can I ask a question, please?
Okay, go ahead.
Yes.
Hello, Satish. How are you?
Yeah, I'm fine.
I'm Mir Mohammed Suleiman Sarwar from Jeju National University Network Convergence Lab. My question is regarding the technicalities of monitoring the network and then diverting the traffic as per the decision of the model. So my first question is that I assume that whenever you are sending the traffic on a specific route, the flow rules are already there, but you are setting up the priority as highest to the route that was predicted the best route by the model, right? So the priority of the flow rules has a limit. And in a route, there are multiple OVSs. So do we need to update each of the OVS in the route by setting up its priority as highest? And what is going to be the priority number exactly? Because the priority number also has a high level. And my second question is that when you are monitoring the path from a source to destination, in which there are multiple paths. So are you actually the data that is used for training the model contains these features of each link in this whole path, or the aggregated data of the path? Thank you. These are my two questions.
Okay. So at first, sorry for that. Actually, let my friend to complete the presentation first, because I think it will take some time. So
okay.
after he completed his presentation, then I will answer the question. Is it okay?
Yes. I think the presentation was ours. That's why I asked the question. Anyways, thank you.
Yeah.
Sorry, no problem. Thank you.
Okay, yeah. So yeah, please continue the rest of the presentation.
Okay, is my audio coming through?
Yes, good.
Okay, so I'm going to continue on. Okay, and you should be seeing my slides. So good morning, everyone. I am Wee King, and I will continue the presentation with the work done in the lab in the project for load threshold identification in wireless networks, and how we make use of a well-established method of AI decision-making and how we implement it into the system. Okay, so one of the main issues we face in wireless networks is the performance as more users connect to the network. Prior work has been done in wireless networks that have shown that an imbalance usually occurs that results in many of the stations flocking only towards certain access points, leaving many others idle and unused. This imbalance makes the network not very well utilized and not optimized. The outcome of this project is then to properly identify the loads in these access points and then perform the load balancing operations only at the appropriate times to optimize the network throughput, especially at this last mile connection point. The issue here is usually identifying the load. It is very difficult because there are many contending issues, such as the different transmission standards, the different bandwidths, the different types of devices, different types of hardware brands, and so forth. Okay, there are many existing methods have been attempted to do load balancing in wireless networks, but most of them have either been proprietary or they break protocol standards, making it impossible to deploy in real life and especially at large scales. Additionally, several methods that have been used are purely simulations and do not accurately depict wireless networks and the issues that face. Many of the issues that I'm trying to bring up is basically playing a role in determining the load in a wireless network, possibly even more than a wired one. Typical loads, like using single metrics like throughput, is usually inaccurate when you're trying to load balance a wireless network, because stations can actually fluctuate between very high demand or being very greedy and consume a lot of bandwidth, or none at all. So when we try to trigger based on loads from the users or based on loads at the access points, it may actually lead to false triggering and may actually result in a load balancing operation that is unnecessary. So estimating actual load is difficult, especially when comparing against the actual user experience on the network, because it makes for very conflicting scenarios that can exist in the network itself. A common method used to trigger load balancers is usually making use of rudimentary if-then-else rules, adding and removing them when necessary in order to fit the situation. A lot of the metrics used in these rules, however, are not really as black and white as they seem. For example, here, if we were just to make use of the single standard 802.11n, we can see that the official standard actually allows us to transmit anywhere between 1 to 54 megabits per second. And they can actually change at any time due to noise, due to interference, so we see. A low bandwidth of 5 megabits here would mean that we're actually at a very low usage in an 11 network, but if we manage to go to 11G network, it can be measured as considerably high because an 11G network only maxes out at around 11 megabits per second. Because of this, the metrics that are often used to measure a wireless network do not actually fall between a very black and white value, but fall into valid ranges with varying weights that have to be applied in order to influence the outcome. Using if-then-else rules in order to create a load balancer will then result in tens, if not to hundreds of different rules that we need to keep changing, updating in order to accommodate different hardware standards and different setups. So an easy way to consolidate all this input is basically to apply a very common method, which is using fuzzy inferencing. The proposed method we're trying to make use of is basically to have a fuzzy load balancing agent that basically piggybacks on the existing network infrastructure to monitor the network and then trigger the load balancer as and when necessary. The load balancer agent utilizes well-known protocols and standards for network communication to control and perform all its operations. 6 logs that are actually being sent by all these network devices are already being used to basically keep and monitor the network traffic, after which the fuzzy load balancer agent performs its calculation to decide whether or not to run the load balancing operation. Once a threshold is met, that is what we're looking for, and decided, then the SNMP protocols are used to control association of stations towards the access points to replicate the requirement of shifting loads between all the access points in the network itself. A simple example of the conflicting outputs we've used in the testing is basically the opposing metrics of station numbers and throughputs. So in this case, high station numbers do not really correspond to high bandwidth utilization, and conversely, low bandwidth may not necessarily mean no number of stations are actually associated. See, these two metrics are actually independent of each other and often conflict with each other, and it's very difficult to make use of them in a if-then-else rules. So a load balancer should only trigger when there are high number of stations and high bandwidth utilizations, but then this also has to be weighted against the current transmission standard being used. So the fuzzy functions can help to approximate rules like this that fall within this fuzzy range in order to trigger the load balancer that we want to have. We have done a simple small scale experiment by making use of 4 wireless stations associating between 3 APs that have been pre-configured. The stations basically repeatedly transfers a 1 gigabyte compressed files between each other, and each station records its own throughput. The load balancer agent works independently, collects the data via 6 logs, and then initiates the load balancer when needed via the SNMP, as I was discussing earlier on. So in a total of 4 fuzzy mapping functions are used in combination to create 16 weighted rules that run in the load balancer. This allows the load balancer to accommodate for any standards between 11B all the way up to 11A currently, or even future standards with very minor changes. From our experiments, we can see that these are the graphs or the data throughputs measured by each station themselves. So at the beginning, you see all the stations are actually trying to download that 1 gigabyte file. You can see that over here, PC3 suffers very low throughput. If I'm not sure if it's shown very clearly on screen, it's basically around 3 megabits per second. And later on, you can see it's going to be affecting because the position of PC3 is basically very near to PC4. It's actually affecting the throughput of PC4. So that's why it actually goes up very low. Okay, so as the transmission continues on, you can see PC1, PC2 manages to reach an average throughput of maybe around 20 megabits to 30 megabits. That's fine. And PC3 is the one that suffers a lot. A load balancer is triggered later on. PC4 is the one that suffers this noise that's being created from PC3, either due to a different type of connection or due to noise that is basically coming from the surrounding environment. The load balancer is triggered somewhere around here, and from that point onwards, PC3 is basically disassociated from the access point, and it begins its process of trying to locate a new access point to connect to. That is where you see PC4 also is affected slightly before it stabilizes at the end. When PC3 finally departs and then associates to a new access point, it stabilizes. You can see the throughput experienced by PC4 immediately improves because it's not affected by the noise being generated by PC3. Later on, we also see PC3 manages to find a new access point to connect to, reassociates, and then continues its download, and then actually manages to reach a very high bandwidth compared to earlier. So you can see at the beginning, it's probably around 3 megabits. It improves all the way up to around 55 megabits or maybe averaging about 40 megabits at the end over here. So we can see from the findings, fuzzy inferencing is very easy to implement and can identify the load thresholds just as effective as all the earlier methods in earlier experiments that has been done before. The thing that we have that has an advantage compared to earlier methods is that the rules are not hard-coded. They fall in ranges and can adapt easily to changing wireless standards and speed. So this single set of fuzzy inferencing functions can represent tens, if not hundreds of if-then-else rules combination, allowing it to be far more flexible compared to earlier methods of doing load balancing in a wireless network. This system also has a good advantage that it actually provides for graceful degradation because it does not change any of the existing standards and protocols. If at any time the agent were to fail, the network basically reverts back to its original 802.11 standards and performs as a normal network. Anytime the basically suffers a problem, the network basically resolves back into its own normal operations without affecting user experience. In the future direction, we want to basically fine-tune and possibly add in additional metrics to more accurately identify the thresholds based on more input metrics in different varying scenarios. The final implementation is proposed to be set in an educational setting where we see the wireless network being used the most and suffers the most degradation due to the way it's being set up and the amount of users that basically have to change between access points as they migrate from class to class. So the education setting will basically propose with 40 stations per venue across multiple venues, across multiple access points. All can be basically controlled by a single agent itself. And at the end, we look at data collection from all these multiple stations in order to show the output results in order to see the effectiveness of the outcome. With that, I've come to the end of my presentation here, and we're open for answering questions. Satish, you want to answer the earlier question first?
Yeah. Mr. Sulaiman, can you repeat the question once again?
Yes. My question was that, first of all, how are you monitoring the paths? Is the data related to the aggregated path containing data of all the links, or the data is of individual links? Secondly, my question was that if you are diverting traffic on a specific route, so you will be setting up flow rules by setting the priority as high over that path that is recommended by the model. So the priority has a limit. I think it has a highest limit somewhere. So what's exactly is going to be the limit? The number of the priority that you set up, and do you set this priority on each of the OVS in the whole path? Thank you.
Okay, thank you for the question. So for the first question, so how we are collecting the network data is actually we are collecting the data of link utilization of every link in our SDN network. So if there is a few switches, the OVS switches have been deployed, so, and then our S-flow collector will actually collect all the metric information of each link that is currently active in our network. So after it collects all the metrics from our OVS switches, then the S-flow collector will actually send those metric to the database. But before it can send the data to the database, all the metric will be undergo some pre-processing where we want to only get the useful metrics that we will be going to use in our traffic forecasting. So all the other metrics that are not very useful will be scrapped off there. So we can, in this way, we can also make the data storage much more scalable as well in our in the InfluxDB that we are currently using, and as well as make the computation much more less resource consumption. So, and then for the second question, we actually didn't went to the model of failover and switchover yet. We are currently now trying to improving the traffic prediction or the forecasting model first, and then only we will be moving to the failover and switchover. Because when we want to integrate the traffic prediction into the failover and switchover mechanism. I think it's a bit more complicated, as you said just now. We also have to we need to consider the SDN controller is who the one will take all the necessary decision regarding the flow rule installation and the flow rule removal from the switches from the data path. As well as not only we can actually change the priority of the flow rule, but we can actually also make the SDN controller to immediately send a notification such as the flow out rule to actually immediately switch the flow loop to the one that we are newly calculated based on the traffic forecasting as well. So we are not only can use the priority, but we can also use other technique as well. So not only priority, we can use other technique as well, such as just now I've mentioned that we can use a flow out rule, or we can also further reduce the current priority of the flow rule that currently been using, or immediately make the flow rule to be overtaken by the new flow rule as well. But that one are still on development.
Okay, thank you. Thank you so much, Satish. Thank you so much.
Yeah. Thank you for the question.
Is there any other questions? No questions? Okay, so I guess it's time to go to the next presentations. Thank you very much. Yeah. Right, so the next presentation is electricity power management utilizing AI in CurioNet by Dr. Sanjay Park from KISTI. Are you ready?
Do you hear me?
Yeah, I can hear you. Okay. So please start there.
Yeah.
Yeah.
Okay. Can you see my presentation?
Yeah.
Yes, we can.
I can see.
Yes, thank you. Hi, my name is Sangjin Park in KIST from Korea. Today I introduce electricity power management utilizing AI in SDN-based networks. Pause. Yeah. First, I briefly introduce CurioNet as NLAN in Korea. We provide high-performance networks and services to about 200 research organizations and universities. Currently, the backbone network upgrade is in progress. So the Dynamic network is expected to provide higher bandwidth at 600 gigabits per single lambda. Also, the international network is expanded. From 2017, we are operating CurioNet S as a SDN-based network. SDN switches are deployed in domestic and international paths, and 3 ONOS controllers are operating for system stability. The architecture of CurioNet S can be divided into 4 parts. The data plane and control plane are deployed as explained in previous slide. And we developed several applications on ClearNetS. The last is an orchestration plane for network automation and the network intelligence. In the orchestration plane, artificial intelligence should be utilized to solve various problems in a complex and dynamic environment. Yes. A typical application is virtually dedicated network for slicing network resource, VDN. VDN is an on-demand service that can dynamically allocate and manage network resources according to user request. These figures are part of VDN list, and the allocated resources are logically isolated with guaranteed performance. In this presentation, I will introduce electricity power management in ClearNetS. Currently, reducing carbon emission to cope with the climate crisis is a global topic. But energy consumption in the ICT domain is expected to increase due to cloud computing, 5G, big data, and AI, and digital transformation. Besides, energy consumption for data center and network operation also occupies a large portion. So there is a need to more efficiently manage network resources. The goal of this project is to reduce the overall power consumption of ClearNetS while satisfying users' requests, especially VDN requests. The VDN requests include a host group that will use resource and the bandwidth and the duration and the maximum waiting delay. VDN requests can arrive anytime, and if there are multiple requests, they enter the queue. Also, the services that exceed the maximum waiting time are removed from the queue. Therefore, the system must solve the real-time scheduling problem within the limited network resource. In terms of energy consumption, the measurement of energy consumption is required, but we are not measure the power consumption of each equipment. So we applied power consumption model through reference papers. When the power consumption model of the SDN switch is divided into 4 categories: base power, port configuration, control message processing, and flow rule processing. Among these, base power and port configuration account for largest portion in energy consumption. To apply the energy consumption model in our test bed in ClearNetS, the specification of switches and the other experimental environment from references were considered. The next step is to collect the data for applying AI algorithm. We built a system for data collection and real-time monitoring. InfluxDB was built to store time series data in long term, and also real-time data can be retrieved by using REST API. Data used for AI include VDN operation, including bandwidth and VDN host, and port state information for each device, including the port speed and port I. Also, the data includes a flow state for each device and processing packets of SDN controllers. We want to conduct AI development by an agile approach. For the first page, we designed the AI-based power management model. We will apply reinforcement learning algorithm. RL select actions according to our dynamic environment to maximize the cumulative rewards. So we define the problem as a Markov decision process and implement a RL algorithm in a relatively simple network environment and service scenario. For the second phase, more complex network and service scenarios are applied for verification through experiments. Also, the AI algorithm is fine-tuned considering the complexity of the problem to be solved. This is the overall architecture of RL algorithm. The RL agent selects the action to be taken based on the current status. That is the topology of kernel S, hardware configuration, VDN operation, and power consumption information. Then the actions are controlled to control the switch on-off mode and VDN operations. The reward function considers the value of energy saved as a reward and violation of the SLA for the VDN request as a penalty. In detail, we defined the MDP model in a simple network environment. As the state space, real-time VDN operation and port allocation of each SDN are used. The action space utilizes creation, deletion, and update decisions per each VDN request. Also, it controls the on-off sleep mode for each switch. And as a reward function, energy saving and 2 levels of penalty are considered. The soft penalty is given when the allocated bandwidth does not satisfy the requested bandwidth. And the hard penalty is given when the allocated bandwidth does not satisfy the actual traffic. To implement the deep learning model, we used TensorFlow and Keras. And the GIM library was used for constructing RL environment. So specifically, we developed a customized GIM environment to apply power management model of our testbed. Hurdles of the current progress is that the number of VDN lists is insufficient to apply the AI algorithm, since few users use ClearNet S, so it is needed to artificially generated VDN request. For this, require the bandwidth and the maximum queue delay and service request frequency and service request period should be considered to reflect the actual service scenario of ClearNet, as the characteristics of each service type can be considered. Various characteristics such as high bandwidth users for data-intensive researcher and low latency users for smart factories, or users who want security and connectivity should be distinguished. Also, the issue of traffic generation according to each generated VDM must be considered. In this regard, we have conducted research on atypical traffic generation and prediction in wired and wireless environments. The complexity of network and service scenario is closely related to the RL design. In simple environment, the lightweight algorithms such as Q-learning can be enough to obtain good learning results. But in a complex environment and service scenario with continuous variables, heavy algorithms, including deep neural networks or policy-based value approximation, should be used. So we will consider an agile approach, applying a lightweight algorithm in an easy environment and a heavy algorithm in a complex environment. In addition, algorithm refinement will be performed by fine-tuning the neural network model or training parameters. So finally, we will build a hybrid experiment environment for testing AI algorithm in the extended network. In future work, we will continue to expand the experiment environment and service scenarios. We will include wireless environments, including Wi-Fi and 5G, that reflect future user demand. Also, we plan to implement actual traffic generation according to VDN request. So we will implement an RNN-based prediction algorithm using time series data such as traffic usage, VDN request, and wireless environment. And we are currently preparing to test power usage monitoring of network equipment and servers. This is closely related to implementation of this project. Also, we are preparing various projects for network automation and intelligence. So we are collecting data generated from networks such as routing, flow, and persona, and we will carry out this project. So I believe that this AI and working group session of this conference will be of great help in carrying out this project. Thank you.
Thank you very much. Are there any questions or comments?
Yes, I have a question. Actually, I want to know about how Indian environment he's trying to mimic the CreoNet environment, like simulation of graphics, like what kind of VDU traffic he how he's going to measure the power consumption in the gym environment for simulation of, like, are you going to use some integer linear programming or Poisson process to mimic the environment?
Yeah, thank you for the question. We implement the system of data collection and data monitoring of our testbed ClearNet S, and we by using this data, we will implement some simulators. We have make some simulators about AI algorithm using just TensorFlow or Keras and the gym environment, and the data is used by REST API. And yes, from now we don't have power manage the graphical UI or any other system for REST power management model.
Okay.
Okay.
Yeah. So are there any other questions or comments?
I have a question.
Okay.
Actually, I think your system is for providing the slicing for some services. Then it can be provided by the VDN, and the slicing can be defined by the MDP. Then I think if you provide the service, every service has its own MDP definition, and that definition should be defined by an operator manually. I cannot hear you. I'm sorry, I cannot hear you. I'm sorry. Okay, then I will contact him personally. Thank you.
Yeah. Yes. So, okay, we should go to the next presentation. Okay. And so the next presentation is artificial intelligence driven control of networks, some challenges and directions, by Dr. Michel from Beijing University of Post and Telecommunications.
I'm here. Can you hear me?
Yes.
Okay. And I will share my screen okay. Okay, can you see my screen?
Yes.
Yes. Okay. Hello, everyone. I'm Xie Kun from Beijing University of Post and Telecommunications. The topic of my speech is artificial intelligence driven control of networks, some challenges and directions. In fact, The application of AI in the network field is very extensive, and it is impossible to involve all of them. So in my talk, I only cover two small aspects and focus more on the routing direction. So this is the outline of the speech, which has three main aspects. First, a little talk about AI-driven networking in routing. And after that, two simple application prototypes of AI in deterministic network and computing-aware network. And let's first look at the routing of traditional networks. There are generally two approaches. One is the shortest path method based on topology, and the other is traffic engineering by dynamic planning based on network states. Both approaches have some limitations and problems, such as the limitation on adaptability for dynamic changes of the network and timeliness for routing calculation, accuracy of the network module, and so on. And these create an opportunity for the introduction of artificial intelligence. And AI-based routing mainly use two machine learning methods, reinforcement learning and deep learning. We know network routing is inherently a decision problem, so it is suitable for reinforcement learning. In addition, the network state and the environment are complex and changeable. So network routing is also a high-dimensional problem, so it is suitable for deep learning. Thus, we can use deep reinforcement learning, aka DRL, to solve the routing problem. And we also have some related algorithms like DQN, DDPG, PPO, and so on that can be leveraged. And this table also lists some of the benefits of using AI to solve routing problems. And we won't go into details here. We mainly focus on the application of intelligent routing in some specific scenarios, such as DetNet, aka deterministic networking, and CAN, aka computing-aware networking. Now let's talk a little bit about some of the techniques I will be covering in this talk. The first is DetNet, which is a technology at the internet layer. DetNet is same as normal networking, but with some features for critical data streams, such as time synchronization, resource reservation, low packet loss reduce, and guaranteed end-to-end latency. One of the technical foundations of DetNet is implementation of TSN, which is out of our discussion. We mainly discuss some routing assurance techniques in DetNet. And the other one is computing-aware networking, aka CAN. It is also called CFN, computing-first networking, but it actually means the same thing. That is the fusion of cloud, network, and edge. CAN is proposed as an emerging network architecture that leverages computing resources distributed in the network. When a client initiates a computing service request, the network can access each computing node's computing power and then schedules the request to the appropriate one through the optimal path. The computing-aware network CAN coordinates distributed computing resources and network resources concurrently, and enables the network to schedule the computing node and route the traffic through desirable paths, so that the users directly access elastic computing resources on demand at any time and anywhere, including the cloud and edge. Obviously, it is a more complex federated parallel planning problem for both routing and computing task scheduling. So AI just has its place here. And the last one is GNN-based AI routing. GNN-based AI routing. As an extended neutral network, it directly acts on graph structure. Graph neutral network, aka GNN, has powerful capabilities for modeling the dependencies between nodes adjacency, and is well suited to deal with NP-hard optimization problems on graphs. As we know, a network topology is just a graph, right? And thanks to Paul Amasan and his group's work, we already know that GNN can just be leveraged to solve the reinforcement learning-based routing problem for different topologies without retraining, which means GNN has a better generalization on topology, different topologies. So DRL plus GNN architecture to optimize network routing is able to generalize over different topologies. Unfortunately, their works haven't considered the deterministic network, .NET scenario, and we will get to that. So this is our first work. As we mentioned before, the DRL plus GNN architecture for network routing optimization is able to generalize over different topologies, and we put it in the context of deterministic network, .NET. So we proposed an intelligent routing mechanism combining DRL, deep reinforcement learning, with GNN to provide reliable and deterministic data transmission services for bounded latency flows in .NET, and both reliability and bounded latency are considered. Since the topology generalization is supported by the module combined DRL and GNN, so the topology changing or oscillation in .NET will not lead to unacceptable routing oscillation or performance degradation. And the deterministic QoS and reasonable bandwidth are promising. The principle is actually relatively simple. So flow forwarding in .NET adopts a resource reservation scheme. In the general DRL-based routing scheme, if there are node failures or topology changing, the currently trained forwarding model cannot immediately adapt to the new topology, which will then lead to a significant decrease in network performance. At this time, the deterministic network will block a part of the flows to ensure the deterministic transmission of some key flows. And if we adopt the DRL plus GNN-based routing mechanism, the losses caused by the above problem will be alleviated to a certain extent. Because DRL plus GNN-based routing has topology generalization, when the original topology changes, the routing module trained by DRL plus GNN is more adaptable to the new topology to a certain extent. At this time, the number of flows that the network needs to block should be significantly reduced, which means that the overall performance of the network will not be unacceptably degraded. So this is our SDN-based deterministic network structure, and out-of-band control structure is adopted here. The control plane in this structure is generally centralized as a controller and separated from the forwarding plane. The controller maintains a global view of the whole deterministic network topology. Routers in forwarding plane communicate with the controller by southbound interface protocols, so that such as overflow, so that the environment state can be obtained and the routing functions can be managed timely and directly. The intelligent agent is running on the controller as a customized network service. The bounded latency flow, aka BL flow. BL flows are scheduled by the well-trained routing policy on the controller, which is continuously updated by the agent based on the rewards data. So this is our GN-based DRL routing architecture. The mechanism consists of 4 logical modules. First is the GN-based DRL trainer. The trainer is here. Second is reward calculator. The third is information database. And the fourth is a flow table calculator for BL flows. When new BL flow demands arrive at the forwarding plan, the triggered routers will update the information of these demands to information database, along with the condition of network resource utilization, such as link bandwidth and caching queue. So information database gathers the current information of demands and resource dates in a proper time interval, then gives them to GN-based DRL trainer as input. With such input, the trainer selects its actions to be applied to environment. That is, the trainer calculates the routing path of their flows as the current routing scheme, and then delivers the scheme to the flow table calculator in controller, which can calculate the corresponding flow tables for BL flows. Then these flow tables will be delivered to forwarding plan. In forwarding plans, the routers forwards all the BL flows guided by flow tables, and the corresponding QoS information can be obtained, including the latency of BL flows, with the help of information database. Such information will be delivered to rewards calculator for calculating the reward to provide feedback to the GN-based learning algorithm about the effect of the recent taken action on policy. According to such feedback, the GN-based learning algorithm can adjust and update itself for a better policy. The whole architecture is designed especially for determinist network with bounded latency considered. The reward function is especially designed considering the bounded latency of BL flows, including the cases that are above the maximum and below the minimum. So the objective of the architecture is to confront the topology changing and node failure conditions from a routing perspective. And we test our mechanism in Mininet, and this is the experimental result. Our aim is to verify the advantages brought by the generalization of our method. We run an experiment using the Giant 2 topology as a DevNet with random node failures, which modify the connectivity among nodes. When a node fails, it is necessary to find a new routing policy that avoids its relative links. As the number of node failures increases from 0 to 4, less paths are available, and therefore the network may typically support less traffic volume due to the traffic blocking, as we said before. We remove up to 4 nodes and evaluate our DQN plus GN model against the state-of-the-art DQN model and the load balancing routing policy. We can observe that as more nodes fail, the score decreases because the total capacity of the network also decreases. Our model score decreases slower slower than the other two methods, which shows that our model is more robust to the topology changes. The traffic volume of the threshold, the traffic volume of the threshold the traffic volume of the scheduled DetNet flow also confirmed it using our model. The remaining throughput in the network is the highest. We also run some experiments to compare the performance of our model with the state-of-the-art DQN model. In figure A, we can observe the box plot with the evaluation results over 1,000 experiments. And figure C shows the CDF from these results. We can see that our model slightly outperforms the DQN solution in the most of the experiments. Then we compare the generalization capacity of our model with the DQN model. They are all trained in NSFNet. NSFNet topology, and then be deployed on Giant 2 topology. So in figure B, we can also observe the box plot with the evaluation results over 1,000 experiments, and figure D shows the CDF from these results. We can observe that our model clearly outperforms the DQN model this time. The results indicate that in this scenario, our model also outperforms the DQN model and achieved more than 25% of performance improvement, which means our model has obviously better topology generalization. Okay, that's all for the DetNet. And second, AI-based bandwidth allocation and computing task scheduling in CAN. This is our second work. So the objective of this work is to select the appropriate compute nodes for the computing tasks while planning network paths for utility optimization. Note that it is not a sequential serial problem. Whether it is routing first and then task scheduling, or first task scheduling and then routing, the optimal result cannot be achieved because the former has a greater impact than the later. So we need to parallel federated planning for both routing and the computing task scheduling. So in this CAN scenario, we use a multi-agent DRL algorithm to solve this problem. That is the SDN-based centralized scheduling by multi-agent PPO, MAPPO. So this is the SDN-based centralized architecture and the mininet-based testing bed. We decompose the computing task scheduling and the routing decision into two action space. Therefore, we use the MAPPO algorithm to simulate the coordinated scheduling of computing and bandwidth resource in the CAN and set actions for them respectively, but share the same critic function. That is, create two agents. One deal with network bandwidth resource, one deal with computing resource. So these two agents share the rewards, cooperate to give joint actions. At the same time, using the shared critic function, each agent optimizes their own strategies and then gradually achieves a common optimality, and finally realize the overall utility optimization. So since the time is running out, and we will not go into details about the specific algorithm model and process, and let's directly take a look at the experimental results. The above figure is the learning efficiency of the algorithm's reward, where the abscissa is the number of iterations. The ordinate is the reward returned by each iteration, and each point on the curve represents the average reward value of 200 iterations near that point. It can be seen from the figure that at the beginning, the algorithm is in the exploration stage, and the generated business scheduling strategy is poor. With the continuous iteration, the average reward will increase and tend to converge after 15,000 iterations. As for the lower graphs, the abscissa represents the number of tasks in each algorithm input. As the number of tasks for each calculation changes, the overall average computation time for computing tasks and the link utilization variance also changes. It can be seen that the performance of the MEPPO algorithm is better than the other three comparison algorithms. One is Floyd, one is nearest, one is random. Okay, that's all for my speech. Thank you very much.
May I ask a question?
Yes, please.
So my first question is, have you considered other types of computing power in your first part of the work? And my second question is, what do you think about the topology scale problem in your research? Thank you.
Okay, thank you for your question. So the first question, the type of the computing power. This is indeed a problem. In fact, in the CAN strategy, in general, different computing power types needs to be considered, such as CPU and GPU. However, our current work is only a simple prototype test and does not consider more complex scenarios. So there is no distinction between the types of computing power. In fact, we can consider increasing the number of agents to solve this computing power type problem. For example, one agent is dedicated to processing CPU computing power, and the other is dedicated to processing GPU computing power. In fact, what is more important is definition of shared evaluation and feedback, and it is necessary to consider the unified weights and measures of computing power, which is another troublesome issue. If the price of computing power is introduced, the problem will be further complicated. So therefore, a lot of future effects are needed in the CAN field, and we will focus on them in the future. And the second question is about, you mean the topology scale, right? So in fact, topology scale is indeed an issue in GN plus DRL based routine decisions. And in our work, there is currently no test for this in our experiments. So I mean, if a node failure occurs in a large scale DetNet, when the number of failed nodes is small, it should not have a significant impact on the current network. That is to say, in this case, our algorithm does not there should be. I mean, our algorithm does not have clear advantages in the if the topology scale is large, but the field number is small. And when there are many field nodes, that is, when the network is disconnected on a large scale, I think we can just think that it has basically become another topology, but this is tested in our experiment.
And thank you for your answers.
Can I ask simply your plan to apply your GNN-based DIR approach to the real network?
Okay.
Actually, I'm asking your plan to apply your GNN-based DIR approach to the real network. Actually, in China, actually there are two the research networks. So I think GNN-based DIR approach can be applied to your some kind of test bed in your research network. And do you have a plan for that?
Yeah, in the future, I will put it into the real environment. But now I just made a mini-net testbed to test this test our module. So it's in our future work.
So the service function chaining could be applied to your approach. Then are you considering that approach?
I'm sorry, I don't quite follow.
Service function chaining. Do you consider to apply the service function chaining?
I don't quite understand your question. I'm sorry.
Okay. Thank you.
Okay, thank you.
Okay. So due to the limitation of the time, we should go to the next last presentations. Thank you very much.
I will stop my screen sharing.
The last presentation is IBM at 10, an AI-driven AI-driven intent-based networking platform for service deployment with QoS assurance by Dr. Afaq Muhammad. Are you ready?
Yes.
Okay, yeah, I can hear you and I can see your slide. Please start the presentation.
Thank you very much. I'm Dr. Afaq from Jeju National University. And today we are going to present our extended work on IBM 10, which is an AI-driven intent-based networking platform for service deployment with QoS assurance. So because of the modern networking technologies and state-of-the-art networking devices, the assurance of the successful operation of the network is the need of the hour. So in order to maintain the underlying services deployed over a network infrastructure. So by following the characteristics of intent-based networking, also known as IBN, in this work, we implement an overlay network topology deployment system, which does three major jobs. One is to collect and analyze resource and network data. Second is to use machine learning for creating an optimal node. And third is to automate the deployment of high-level policies for actions related to service provisioning on the most optimal node through overlay network topology deployment. So this system is going to be deployed on the Trans-Eurasia Information Network, which is also known as TAN, where the abstraction will be provided by IBM to achieve the complete network automation. So in order to automate the overlay network topology deployment at 10, we set some goals. We had set some goals in the beginning of this project, in beginning of this work. So the primary goal was to create a data set, a network and compute traffic data set, using real-time processing of data. And the second goal was to predict an optimal node using machine learning algorithms. So in this case, we use supervised machine learning algorithms. The third was automatic execution of overlay network policies by leveraging intent-based networking management layers, and then a real-time monitoring system for the collection of network and compute data and assurance of network devices. So eventually, our goal was to implement a scalable system that operates in a closed loop manner by obtaining information from the infrastructure layers, the underlying infrastructure layers, and processing, analyzing, and applying network policies directly from the management layers back into the infrastructure. So for this, we describe our project in 4 major sections. The first section is network infrastructure, in which we have traffic experiments for data collection, and then we use some state-of-the-art monitoring tools, which is Perf Sonar and Prometheus, which are configured in nodes connected to TAME. And then we have the most important part of this project, which is the ML-driven optimal node prediction. In this section, we do the data processing of network and compute raw data, and then the data is stored in Prometheus for optimal node prediction, machine algorithm training and testing, and then labeling of incoming traffic data for real-time optimal node selection. We also do monitoring and analytics. Because of these monitored data, we provide the data to the ML module. So we use Prometheus and Grafana for showing the network and connected devices status in real time. And we also use intent translation engine, in which we do the policy creation and execution by this engine to establish overlay network connection. So we describe our overall system in this slide, where we have a closed loop approach, IBN approach, for intent assurance to end users upon their request, upon their service request. So first we have a real-time monitoring system here for the collection of data. Then we have a machine learning system for service provisioning on an optimal node. And then we have here the IBN system, which is the automation of configuration creation and management of overlay network with this system. And then we deploy the configurations on the underlying infrastructure, which is OpenStack in this case. And finally, we establish tunnels, or we establish the overlay network between different clouds. We considered some implementation scenarios in the beginning of this work. So the first scenario that we considered was the most basic scenario, in which the user submits an intent without mentioning any QoS requirements and without mentioning any service providing node, or also called SPN. So basically, many clouds here and instances host the requested services, and IBN selects any available node for intent assurance of the user. So this is kind of a best effort model in which we do not provide any QoS parameters. So the second scenario we have is if, for example, the requested service is available at the requested node. For example, if the requested node is here Jeju in Korea, the service is provided from this node. However, if the service is not hosted at the requested node, but is available at some multiple cloud instances, the service is then shared or replicated to the desired node, which is also the source node, from the most optimal node, which is the destination node, through the Genève tunnel, which we can see here in orange line, the Genève tunnel. So to this purpose, the Genève tunnel is first established, then the service is replicated to the desired node. So in this case, for example, if we have multiple cases like this, eventually we will have a topology in this scenario where we will have established tunnels using this approach. Scenario 3 is similar to scenario 2, but it is different in a sense that in scenario 3 we have all the Genève tunnels pre-deployed in the form of either star, mesh, or some random topology. So we have already these pre-deployed tunnels, and then we replicate the service from the source node to the destination node, or the most optimal node. Then the experimental details are described one by one. We first consider the monitoring and analytics to collect the data to create a data set, as I mentioned in the previous slide. So for this, we used Perf Sonar and we used Prometheus. So Perf Sonar was used to collect the network data statistics, and Prometheus was used to collect the compute data. So for example, we have 2 clouds deployed here at different locations, and we can see here that Perf Sonar is collecting network data, which is shown as in the green dashed line. And we have, for example, iPerf UDP and iPerf net TCP and different network statistics which are collected here, and then they are given to Prometheus database using Prometheus push gateway. And similarly, the compute data, for example, CPU or RAM, it is given to the Prometheus database using the Prometheus proxy server. So eventually, we have a data set which have the Perf Sonar matrix containing the network statistics, for example, speed, bit rate, congestion windows, jitter, and so on. And we also have the Prometheus matrix, which are the compute matrix, and they consist of, for example, CPU, RAM, and other compute statistics. Then we also created an IPN portal, which is responsible, which gives the authority to admin and site manager and general user to manage the intents and to manage sites and manage the nodes of each location or of each node. Then we also have the IBM schema, which is used in the intent translation tool, and it shows the entities and the relationship between these entities. Then we have the most important part of this project, which is the machine learning procedure. So first of all, we had the raw data, and then we applied some data processing techniques. We applied vectorized data and then vectorization of data, and then we did the scaling of data in this first part, which is the data processing part. And then we labeled this data by providing some labels. For example, the nodes names were given as labels, for example, Korea, and for KR for Korea, MY for Malaysia, and other sites we have in the project. So after the labeling of data, we then selected some features in the data, and then we applied the supervised learning models. So since our problem set is of the classification, so we use the classification algorithms, which I'll be describing in the coming slides. So we split the data into 2 parts. One was 95% for training, and 5% was used for model testing. Then we have in the results, we first had the raw data, which is shown here. It is in this form. It has different rows and columns, but it was all raw data. It didn't give any meaning at that time. Then we pre-processed the data, we cleaned the data, and when we visualized the data, we had the data in this form, which is without any missing values. We have here around 10,000 samples, and we have rows, also called rows, and we have around 24 columns, which are shown here, also known as features. So we use this data set and provided it to the machine learning algorithms, and we trained those algorithms with this data set. So we used 5 classifiers in this work, or 5 machine learning models. The first one was used extra trees classifier, and then we also used linear discriminant analysis, also called LDA. We also used ridge classifier, naive bias, and KNN, also called K nearest neighbors classifier. So the performance of these models was varying, was different from each other. For instance, the best performance that we got was of the X+AI classifier, which can be seen from this confusion matrix, and the least performing algorithm in our case was the KNN algorithm. So then we can also see here the comparison of these models. We compared the mean accuracy. So we can see from this table and also from this bar chart that the accuracy of the ET classifier, which is X+AI classifier, is around 92% here, and the standard deviation of this accuracy is the least. So it's the best performing algorithm among all the algorithms, and we can see that the KNN is the least performing here, which is showing the mean accuracy of around 54%. And the other algorithms like linear discriminant analysis, also called LDA, or rich classifier or naive Bayes, they somehow show the performance in the middle of the X+AI classifiers and KNN. So the X+AI classifier outperforms, as shown in this slide or from this graph, you can see outperforms all other classifiers in terms of accuracy and other performance metrics. We haven't shown other metrics here. For example, we had the recall, we had the F1 score and different metrics also, but we are showing the mean accuracy in this slide. So it outperforms all other models in terms of all the performance metrics. So using this X+AI classifier, we selected the optimal node for service provisioning, and then we created the tunnel between the source node and the most optimal node selected by this machine learning algorithm. So to conclude my presentation, we use intent-based networking and approach, and we applied this to 10 network for overlay network topology deployment because IBM has machine learning, so we also use machine learning in this approach. So this approach taken for this research considers the multiple qualities that brings intent-based networking to modern networking systems, such as network abstraction, orchestration, automated implementation, state awareness, assurance, and remediation, which can be realized for building more resilient systems. In addition, this approach considers a real-time processing architecture for handling continuous streams of compute and network data and processing them in real time using high-performance tools such as Perf, Prometheus, and PySpark. So the evolution of this system is assured by the constant collection of processed and raw data, which can be used for to furtherly enhance the implementation of ML algorithms or other AI techniques that we'll be considering, because in this approach we considered some traditional machine learning techniques, but in the future, in our future work, we are going to consider some sophisticated deep learning techniques, and we will check the performance of our system, like how the deep learning algorithms perform with our system. So thank you very much for your attention. That's all from my side.
Thank you very much. Are there any questions or comments?
Yes.
I would like to know one thing.
Yes, sure.
When you allocating the data set, why did you use 95% for training and 5% for testing? Generally, we know that it go with 80-20 rules, right?
Yes, generally, like it's also 70-30, sometimes 80-20. But we actually also tried with the 70-30, but with because we also use the cross-validation method here. We use the 5% for testing, but we also use the cross-validation approach to validate our performance of our model. So that's why we just put 5% for testing, and we also perform the cross-validation.
So you mean it will get your optimal solution for that?
Yes, it gave us optimum results when we chose 95% for training and 5% for testing, and this was chosen randomly. because we were performing the cross validation also.
Oh, I see. Actually, if you go with open data, I really wonder what will happen for your model.
You mean if you consider like 70-30 ratio or 80-20 ratio?
No, I mean, out of your data set, if you text with open data,
Okay.
open data, what will happen to your model? Yes.
Yes, you're right. Because if we increase the unseen data to 20% or 30%, you're right that how it will perform. We will have a look at that as well.
Yeah, that's why I think the testing data 5% too few. In my opinion, I'm not sure.
Yes.
Okay. Are there any other questions or comments? Okay. Can I ask one question? I guess you, from your experimental results, the classification model, X+AI classifiers is the best performance. Yeah. And would you tell me the detail of the X+AI classifiers briefly?
Details in terms of the performance matrix, you mean?
No, just the method of the X+AI classifiers. What kind of classifiers?
Yes, it's actually the modified form of random forest.
Random forest type?
We have some extra, sorry?
It's a random forest?
Yes, it's the modified version of random forest algorithm.
Okay. Yeah, thank you very much. Any other questions or comments? Okay. Yeah, thank you very much.
You're welcome.
Okay. So yeah, that's all for the this second session. So Professor Bachan-san, would you summarize this session? Okay.
Okay. Thank you for all contribution of the all speakers and attendees. Actually, we had 2 sessions by online this time also, but I wish we could see each other by offline in the next time. APAN 55. The venue for the APAN 55 is the Nepal, and I hope we can have a better the working group sessions. Thank you very much. Okay. We can finish our sessions. Thank you very much. See you again.
Thank you. See you.
Thank you, Professor.
Thank you.
Sure.
See you.